Mr. Tarrou, in this calculus lesson, we're going to do 4 examples going from easy to hard, learning how to represent a function by a power series. Now, in our 4th example, the hardest of these 4, you're going to see why our previous lesson was finding derivatives and integrals of power series, because it's going to help us finish that example. But starting off easy, we have the geometric series, and defining what we're doing really, our geometric series where we have sigma, or the summation of a times r to the n power, where n starts at 0 and goes to infinity, is equal to a over 1 minus r when the absolute value of r is less than 1. Remember that sum of an infinite geometric series that we first learned in pre-calculus. This formula from pre-calculus, which by the way also allowed us to rewrite repeating decimals as a fraction, helps us represent functions as a geometric power series. You know, we've been spending this chapter so far learning how to determine if a series converges or diverges. Now we're going to start developing our own series from a given function. Now we want to find a power series for the function centered at C and determine the interval of convergence. Now it says example, but this is really what we're doing in all of our examples, all 4 of the examples. Come up with a geometric series which estimates a given function centered around a particular value. And in this case, we're going to do f of x is equal to 1 over 1 minus x, and we're going to be centering our geometric series at 0, our geometric series again, which is going to estimate values of this function. Well, I said we're going from easy to hard. I mean, look at our function. We have f of x is equal to 1 over 1 minus x. And this relationship with creating a geometric series from a, or that will represent a given function, a over 1 minus r, we're already in that exact pattern. We have some constant of a, so we're going to let a, or identify our first term in this geometric sequence, or series, excuse me, as equal to 1. And 1 minus r, well, we have already a 1 minus x, so our r value is going to be equal to x. Cool, so this is, again, about as easy as it's going to get. Our geometric series that will represent this function centered around 0 is going to be the summation, or sigma, where n starts at 0, goes to infinity, if we want an exact approximation, if you will, a, which is equal to 1, times our r value, which is equal to x to the n powered. Now, if we do a little bit of an expansion of this, of course, just to, I don't know, review what this is going on here. We have n is 0, so we're going to have 1 plus, now we're going to let n equal 1, so we have x plus x squared plus x to the third. Our upper limit here is infinity, so this is going to keep adding until we get to x to the n, and we're going to infinity, so, you know, just never stops. This geometric series will estimate the value of this function to whatever amount of accuracy you want. You just keep adding terms. If you let the upper limit goes to infinity, you could say the approximation is exact, centered around 0. But this geometric series is not going to give you a valid answer all the time, right? An infinite geometric series only gives you a valid answer when that series converges, when the absolute value of r is less than 1. So when is this series going to give us a valid answer? Well, the ratio, the r value, this absolute value of x has to be less than 1. We're finding an interval of convergence. Actually, not an interval of convergence, but a radius of convergence. We'll clarify the difference there in a second. So the absolute value of r, the absolute value of x, has to be less than 1, so x has to be less than 1 when you take the absolute values of both sides, or the well, how do you rewrite this so there's not an absolute value function? So x has to be between -1 and 1. So when x is between -1 and 1, this geometric series is going to give us a valid answer. Now, we don't need to test the endpoints of this radius of convergence to find the interval of convergence, because we're already given that. We already understand that condition with the geometric series. Once we recognize that this is a geometric series, we know the absolute value of r has to be less than or equal to 1. So, we're not looking for when the absolute value of r is less than or equal to 1. Those endpoints are not going to work. So even though I'm saying the radius of convergence, because we're working with a geometric series, we know that those endpoints are not going to work. So actually, this is going to be, I don't understand that we don't need to test those endpoints, the interval of convergence from -1 to 1. So for our second example, we have f of x is equal to 5 over 3x minus 1. Now this time we want a geometric series centered around 2. We want a geometric series that estimates values, will give estimate of values from this function around that value of 2. And we already know over here, like we did over here, with this geometric series is going to estimate values for this function as long as we're within -1 to 1, and you see that center of 0 in the middle of that interval. What are we going to do? Well, how are we going to derive a geometric series that represents the given function? We're going to make that given function look like this. Look like that infinite sum of a geometric series formula we learned in pre-calculus. Make this pattern show up inside that function, and you can come over to that geometric series notation. Okay, well, we also need it to be centered at 2. So we need our geometric series centered around x equals 2 or x minus 2. We need an x minus 2 pattern to show up in this denominator, basically in the second term. So we have a 3 in front of the x, and if we have a coefficient of 1 here in front of this x, just to highlight that we needed an x minus 2 parentheses in the denominator to see that center or have that center at x equals 2, we would have to pull the 3 away from, factor it out of the x. Well, how's that going to happen? We need a 3x minus 6 in the denominator. So we're going to have 5 over negative, well, let's see here. No, we're going to do this. We're going to do 3x minus 1. If we just subtract 5, we'll have, from -1, we'll have a -6. Well, if we're going to, bring in a subtraction of 5 in the denominator, of course, I don't want to change the value of this fraction. We're going to need to balance that out. We're going to balance it out by adding 5. Maybe I should just write plus 5 over here, but I'm trying to make that constant, or that value of 1 minus r, show up in the denominator. So I'm going to write that plus 5 out here. So a plus 5, a minus 5, that cancels out or balances out. We have 5 over 5 plus 3x minus 6. Factor out that 5. Factor out that 3. Sweet. Now we get f of x is equal to 5 over 5 plus 3 times x minus 2. We have that x minus 2 factor in the denominator, showing that we're getting close to having some function, with that centered at 2 idea in there. But it's a. Now the numerator of this infinite geometric sum, infinite sum of a geometric series, can be anything, but the first term of the denominator has to be equal to 1. So we see that 1 minus r pattern. So we're going to multiply the numerator and denominator by 1/5, or divide both top and bottom by 5. And we have 1. Okay, I didn't need a 1 in the numerator, but we have it. 1/5 times 5 is 1. Now we have plus 3/5 times x minus 2. Now we're looking at f of x. Okay. So we've distributed our 1/5 through the numerator and denominator, and we have 1 plus 3/5 times x minus 2. Well, that's almost the pattern we have here, but we need to see 1 minus r, not 1 plus r. It needs to be an exact match, that pattern. So we need to rewrite this so that there's a minus there, and we can do a minus negative 3/5, or we can factor a negative 1 out of this x minus 2 to have a negative there, or a 1 minus something. So we're going to factor a negative 1 out of x minus 2 and have 1 over 1 minus 3/5 times 2 minus x. Okay, there we go. Now, we can see that we're in this pattern of a over 1 minus r, that our a value is equal to 1, and our r value is equal to 3/5 times 2 minus x. So our series, our power series, that's going to represent this given function centered at 2 is going to be the summation, or sigma, where n starts at 0 and goes to infinity, of a1 times r 3/5 times 2 minus x to the n power, right? A times, or a divided by 1 minus r is equal to the summation, where n starts at 0 goes to infinity, of a times r to the n power. Well, like we mentioned with the first example, this series is not always going to represent this function. This series is only going to give a valid answer when it converges, when the absolute value of r is less than 1. So for this to give a valid answer, it needs to converge. And for this to converge, then we need the absolute value. I'm going to find the interval of convergence. When are you allowed to use it? Basically. And I'm running out of room. The absolute value of 3 over 5 times 2 minus x. The absolute value of that has to be less than 1. And I'm running out of room. I should have moved this up here. We have 3 over 5 times 2 minus x has to be less than 1 or greater than negative 1. Multiplying both sides, or dividing both sides by 3/5, we have negative 5 is less than 2 minus x. And I'm just going to run out of room. Is less than 5/3. We're going to need to subtract both sides by 2 and then divide by negative 1. But I'm running out of room and I don't want to leave you some messy notes. Let me just step off, erase some of this, write this out neatly, and we'll move on to the third example. Bam! Example number 3. F of x is equal to 5 minus x over 5x squared plus x minus 1. Stepping it up, we don't have just a constant in the numerator, so we need some more information. Operations with power series. Let f of x equal the series of a sub n times x to the n power, and g of x equal the summation, or the series b sub n times xx to the n power. Well, if we have a multiple here on, a constant here, multiple on the x, f of k times x, we have the summation, where n starts at 0 and goes to infinity, of a sub n. That k comes in here as a k to the n power times x to the n. We have f of x to another power is going to be equal to the summation, or sigma, where n starts at 0 goes to infinity, of a sub n. And then we have that x to the n that was already in our geometric series, times that power which is on the x here. So we have x to the n times capital N. And then we have f of x plus or minus g of x is equal to, so if you're adding or subtracting functions, basically, you can add or subtract those series, and it comes out to sigma of where n starts at 0 goes to infinity of a sub n plus or minus b sub n times x to the n power. We're going to be using that as we finish this example number 3. Now, these operations with the power series, they can change the interval of convergence, so recheck that when you're done setting up those series. And the interval of convergence is the intersection, for our last one here, the interval of convergence is the intersection of the intervals of convergence for our series a sub n times x to the n power and our series of b sub n times x to the n. So these operations will change the interval of convergence, but on the third one specifically, you're looking for the interval, or the intersection of convergence for two individual series. So how do we get this numerator to be a constant? Well, we have a degree of 1, a polynomial with a degree of 1 in the numerator, and a polynomial with a degree of 2 in the denominator. And if we pull this apart with partial fractions, we'll have our constants in the numerators like we need. So, get my fancy picture in picture here. We've got 5. Let's move this over a little bit so I'm not so cramped. We've got our 5 minus x. Now, we can factor this 2x squared plus x minus 1. I usually go through a little bit of a process for factoring quadratics with the leading coefficient other than 1, but this is just these are all prime numbers. So we're having 2x and x. We're going to need a plus or minus. The middle term is positive, so plus 1 and minus 1. We want to pull this apart into basically unadd. We want to pull this apart to two separate fractions, so we have those constants in the numerator. So we're looking at this as the sum of a over 2x minus 1 and b. Little partial fractions practice. Learned this in pre-calculus, and we've already used it in our calculus class through the year. We're going to multiply both sides of this equation by 2x minus 1 times x plus 1, and we're going to have 5 minus x is equal to a times, now the 2x minus 1 is going to cancel out, so times x plus 1, and b times 2x minus 1. You can hear how much nicer this blackboard writes than this green one. We want this is effectively an identity. The two sides here need to be equal regardless of what x is equal to. So to figure out what a and b are going to be, we're just going to let x equal values that are going to allow one of these two terms to cancel out. So if we say let x equal negative 1, we've got 5 minus negative 1 is 6. Negative 1 plus 1 is 0, so the a is gone, and we have b. 2 times negative 1 is negative 2, minus 1 is negative 3. That's going to give us a b value when we divide both sides by negative 3 of negative 2. If we let x equal, well, this needs to be 0, so that needs to be a 1 minus 1 is 0, so we're going to let x be 1/2. We're going to have 5 minus 1/2, which is going to be 4.5. And our a, and that's going to be, of course, well, 9 over 2. 2 times 1/2 is 1, minus 1 is 0. So now we have a times 1/2 plus 1, which is 3/2. Multiply both sides by 2 over 3. And we got a is equal to 3. And just so I don't do a nice long example with a careless or small sign error or something to that effect that I'm unfortunately very prone to do, we have b is negative 2, a is equal to 3. So this can now be rewritten as a, which is 3 over 2x minus 1. And b, which is negative 2, so really plus, but minus 2 over x plus 1. All right. Removing picture in picture. f of x is equal to 3 over 2x minus 1 minus 2 over x plus 1. Well, we can now we're really close to like those first examples. We can write this as 3 and, well, maybe negative 3, and then we have a 1 minus 2x. And over here we've got 1 minus 2 over 1 minus negative x. Now this means that we're going to have, let's do a plus negative up here anyway. So this means that we have an a value, which is equal to negative 3, and an r, which is equal to 2x. Here we have an a sub, let's call it a sub 2, which is equal to negative 2, and a r, which is equal to negative x. Now that's bothering me here because, oh no, you can have an r value that's negative, of course. So we have f of x is equal to the summation where n starts at 0 and goes to infinity of a, which is negative 3, times r, which is 2x. Now, of course, it's a times r to the n, plus series where n starts at 0, goes to infinity of a, which is negative 2, times r, which is negative x, also raised to the n power. Now again, just checking my work. Okay, now we can go ahead and we're going to talk about and show how we combine these two series, using, get it in this notation here where we have f of x plus or minus g of x. We had f of x is equal to, now this is two functions subtracted together, or added if you want to change the notation. We want to write that as a single series, but geometric series. But we need to look at the interval of convergence for each of these geometric series. When are they going to give us valid answers? When are they going to converge? Well, for our first one, our interval of convergence, let's put this up here, I see for interval of convergence, the absolute value of 2x is to be less than 1, so we're looking at 2x is less than 1 and greater than negative 1. We're looking at x is less than 1/2 and greater than negative 1/2. And so for our second series, we have the absolute value of negative x. Made a sign error, my first take for here. We have the absolute value of negative x is equal to negative 1. Well, of course, the absolute value of negative x is, that ratio doesn't matter if that ratio is positive or negative. We're looking for the absolute value of that to be less than 1. So we're looking at x is, the absolute value of x is less than 1. So we're looking at x is less than 1 or greater than negative 1. I just effectively took the absolute value of negative 1 there. Well, the first series has an interval of convergence between negative 1/2 and positive 1/2. The second geometric power series has an interval of convergence of negative 1 to positive 1, but both of these geometric power series are within the same function, so they both have to be defined, they both have to be given valid answers, they both have to be, we're looking for an interval of convergence for where both of them are working. So our final interval of convergence is right here, the intersection of our two interval of convergences is negative 1/2 to positive 1/2. Now, how do we bring these together? Well, I mean, we can simply write this. Summation going from 0 to infinity of negative 3 times 2x to the n plus negative 2 times negative x to the n. But that's kind of ugly. Can we just get, some kind of constant here with a x sub n at the end? Can we make this so that we can get that out of there? Well, we can write this as n going from 0 to infinity of -3 times 2 to the n times x to the n. I don't really know why I wrote that in parentheses there. We have a plus 2. I want to be able to rewrite this so we have a bunch of stuff, a factor, in front of x to the n. I want that negative out of there. So we're going to write this -2 times -1 to the n x to the n. Ah, okay. So we can now factor a x to the n out of there and say that we have the sigma, or the series, the summation, where n starts at 0, goes to infinity, of -3, 2 to the n, times 2 to the n. I don't like writing plus minus, so -2 times -1 to the n power, and then basically effectively factoring out that x to the n. So this geometric power series, and these are all constants. If you were to expand this out, letting n equal 0, n equal 1, n equal 2, so on and so on, this is just going to take on some kind of constant, and then we have x to the n power. That's your variable right here. That is going to represent, this geometric power series is going to represent our original function here, 5 minus x over 2x squared plus x minus 1, that centered about 0, around 0, and this will give a valid answer. This will converge as long as x is greater than -2 and less than, as long as x is greater than -1/2 and less than 1/2. I got one last example coming up right now. No. It's our last example, number 4. We have f of x is equal to the natural log of x squared plus 1, and we're looking for a geometric power series that represents this given function. I didn't write it, but centered about 0. Well, how does this example look different than all the other ones, other than I told you at the beginning of the video we'd go from easy to hard? Well, it's got a natural log function in it, and it doesn't look like a rational function. It's not a fraction. We're not gonna look at that and go, well, a is equal to and r is equal to, because there's no a over 1 minus r. There's no fraction bar. But the derivative of the natural log function is, the derivative of the natural log of u is u prime over u. So we're going to take the derivative of this, and we have f prime of x is equal to u prime over u. Oh, well, nice. We now have a fraction bar. Can we get that written into some pattern that allows us to see a over 1 minus r and identify some values and get into a geometric power series? Well, we've got a variable in the numerator, so let's get that out of there. So we have 2x, 1 over, and there's a binomial in the denominator. So if we can get this to look like 1 minus r, well, we already have a 1, not that, I mean, the numerator doesn't have to be 1, but we need a 1 minus. Oh, well, we'll just write 1 minus negative x squared. Now we're looking at this and we're going to say that a is equal to 1 and r is equal to negative x squared. Cool. Well, now we've got 2x times the summation, or sigma, where n starts at 0 and goes to infinity, of a, which is 1, times r, which is negative x squared, a times r to the n. And you see how we have like some powers in here? We're using that, we're starting to get into that second operation of geometric power series, which means that when we get to our final answer, we're not going to just say the absolute value of r is less than 1 and have some easy interval of convergence. I hope it's not too difficult, but we're going to have to actually work through the ratio test and test the endpoints to find our final interval of convergence, because we're starting to use some of those operations of geometric power series. Okay, let's go ahead and, now that we have gone from the function natural log of x squared plus 1, took the derivative. Could see that a over 1 minus r pattern. We're into some kind of series notation. Let's bring the 2x back in here, and we have 2 times 1 is 2. Well, I'll just write 2x. And here we got something going on. We got negative x squared to the n power. Because I want to have a constant first term and then some kind of, something to an n power. So we're going to need to pull this apart a little bit. Let's write negative 1 to the n power and times x to the 2n power. Oh, nice. Now that's going to allow us to, put together the 2, not the 2 to some kind of n power, but 2 times negative 1 to the n, and we have x times x to the 2n, giving us x to the 2n plus 1. Sweet. Now, if we go ahead and expand this, let me just double check I haven't done something silly here. Okay. Now, that's great. We are in some kind of series notation. But, it's not a geometric series for f of x. It's a geometric power series for f prime of x. Now that's where our skills come in that we just learned in the previous section, derivatives and integrals, taking them, derivatives and integrals of power series, or just a series. So, yeah, so we need to remember that f of x is equal to the integral of f prime of x dx. We need to, take the integral of this geometric power series. Well, our 2 times negative 1 to the n is we let n equal 0, n equal 1, n equal 2, n equal 3, so on and so on. This is just going to create our constants of our terms, and we're really in a course of, using the power rule to integrate that thing with that factor with the variable base on it. So we have f of x is equal to the integral of this. I'm just going to write sigma with going to infinity and starting at 0, or 2 times negative 1 to the n power, our x. Now we're going to simply just take this power, increase it by 1, and then divide. So 1 plus 1 is 2. Now we're going to divide by 2n plus 2. I should have made my sigma notation a little bit bigger. We can do a little bit of cancellation here and say that f of x is equal to summation, sigma, n 0 to infinity of negative 1 to the n power times x to the 2n plus 2 over, I forgot something, didn't I? What did I forget? My constant of integration, right? I just did an indefinite integral with this series, which means we need a plus c. For goodness sakes, don't forget that. Well, two things. You want to, you might be doing, your integration of your series term by term, or you might just, do what I did, use the power rule. But let's make sure it's right. Let's expand these two series out, make sure that it's matching up, that this actually is indeed the integral of this series, and then maybe that will allow us and help us to determine how to deal with what is c. So if we let n equal 0, well, that's going to be 1. So we have 2 times x to the first. Now if we let n equal 1, well, now we're going to have a negative here. So negative 1 to the 1 power. So we have negative 2. And then we have x to the third power. If we let n equal 2, that's going to be positive. We have a plus 2. X to the 2 times 2 is 4, plus 1 is 5. And then minus 2, x to the 7th, and then so on and so on. Here we have n equals 0, that's going to be positive. So we have x squared over 1. We have n equals 1, that's going to be negative now. And that's going to be 2 plus 2 is 4. 1 plus 1 is 2. Let n equal 0, 1, 2. That's going to be positive. That's going to be 2 times 2 is 4, plus 2 is 6, over 3. Now we have 0, 1, 2, 3. Negative 1 to a third power is negative. Boom. We have x, 2 times 3 is 6, plus 2 is 8, over 4 plus c. Okay, so we have two things that are nice here. Look, if we integrate this, if we raise this power by 1, x squared, 2 divided by 2 is 1. If we raise this by 1, we get 4. Divide by 4, 2 over 4 is 1/2, and it indeed is negative. We have a positive. We have x to the 5th. Divide by 6, 2 over 6 is 1/3. So yeah, we can check term by term and make sure that our new series is indeed that correct integral. What about the plus c? Well, f of x is the natural log of x squared plus 1, so the natural log of x squared plus 1 is equal to x squared minus 1/2 x to the 4th plus 1/3 x to the 6th minus, and then so on and so on. Well, this needs to always be true. Now, okay, it's not always true. We need to find the interval of convergence. You know, when is this power series going to represent the given function within its interval of convergence? That's the only time it gives us a valid answer. But within that interval of convergence, we always, you know, the point of this is to always have this be true. At least if you go to infinity, the approximation we get, if you just want to do 2, 3, 4 terms, you can not get an exact approximation. But we're trying to find a geometric series centered about 0, and if we just let x equal 0, something nice happens. I mean, x equals 0 has to be within the interval of convergence. It's the center of our power series. So we have the natural log of 1, and now as we put 0 into each of these terms, they're all going to become 0. So we have 0 plus c. Well, the natural log of 1 is 0. So c is going to be equal to 0. Well, that's nice. We can kind of just forget that it's there. Boom. So we have f of x, which is the natural log of x squared plus 1, can be represented by this series, this geometric power series, where we have the, at least that's how we got through it into this series notation. But we have for the sigma notation, where n starts at 0, goes to infinity, negative 1 to the n, times x to the 2n plus 2 over x plus 1. Well, you just saw my previous page of notes. If you start using some of these operations of power series, the interval of convergence may change. So we need to now look and review some of our skills from earlier in the chapter and find the interval of convergence of this series. But I want to make sure I don't run out of time on the camera. Clean this up. We'll get that done. We're going to work through the ratio test to find our radius of convergence, and then test the endpoints to find our final interval of convergence. So we have our series. We're going to set up our ratio test. Now, we've spent a lot of time learning this recently. I'm going to kind of do a slightly cliff-noted version here, but we're going to set up the absolute value of our a sub n plus 1 over a sub n. So we have negative 1 to the n plus 1 times x to the 2 times n plus 1 plus 2 over n plus 2. So our a sub n plus 1 over a sub n. Go ahead and flip this up. Get some cancellation going on here. We got one more negative 1 in the base of negative 1 in the numerator than the denominator. We have x to the 2n plus 2 and x to the 2n plus 4. So there's 2 more bases of x in the numerator versus the denominator. And of course the n plus, we're going to let n go to infinity here for a second, but nothing's going to cancel out. So we have the limit as n approaches infinity, the absolute value of negative 1 times negative 1. We have an n plus 1 and an n minus plus 2 times x squared. Now as you let n go to infinity, and you can prove this all kinds of ways, L'Hopital's rule, whatever, but this is going to cancel out to be infinity. Well, it's going to come out to be 1. So this is going to come out to be negative, the absolute value of negative x squared. Now that needs to be less than 1. For this to converge. And let me just check my answer here. The absolute value of negative 1 is 1, square root. Now, remember, we have a center of 0. We find a geometric power series centered about 0. And a radius of convergence, which is equal to 1. You can see all that information right here. We need to test the endpoints. Now here's what I'm going to honestly just cheat a little bit. If you check the endpoints to find your final interval of convergence, if you plug x equals negative 1 in here, you're going to have negative 1 Now, 2n plus 2, this is always going to be even, and negative 1 to an even power is always going to be positive. Here's I'm going to kind of just get a little cheap on you. When you do the alternating series test on this, you're going to see that it does indeed converges by the alternating series test. And when you let x equal positive 1, well, positive 1 to the 2n plus 2 is still going to just be positive 1. But just to write it, and we've already shown by the alternating series test that this indeed does converge. So your final interval of convergence is from negative 1 to 1. So this power series does represent the natural log of x, what was it again? X squared plus 1. This power series centered about 0 will represent this function on the closed interval from negative 1 to 1. I'm Mr. True. Bam! Go do your homework.